Welcome to the part 2 of the open loop control of three-phase controlled rectifier. So in the previous video we saw how to simply simulate this three-phase controlled rectifier by giving the value of firing angle alpha manually. In this M file we had the definition of variables and control parameters, and in the Simulink model we had implemented the control of the converter. Let's analyze further with different other angles. So if the angle is less than 90 degrees, then we had the rectification mode of the converter. In case we have an angle greater than 90 degrees, let's start with 90. So ideally we should get an output voltage average value to be 0 volts. Let's check. So for your information, we had the resistive load here connected to the DC side, and it's now being simulated for an angle of 90 degrees. Let's check the values here. It's for angle of 90 degrees. As you can see here, we don't really have the value of the output DC voltage to be 0 volts. So if we take the time period here and measure the yellow curve, you see we have about 271 volts, which is not what we're expecting. Now the reason behind is that since we have a closed circuitry on the DC side, the current is being flown, and this voltage is resulting, since we don't have an active source on the DC side. I can check this if we have really the output voltage to be 0 volts. Let's remove the source for a short while and check. So I rerun the simulation and then bring back the output curve window. So it's clearly seen here that we have the connection voltage here, RMS 1.5 kilovolts, and the DC voltage, which is on the yellow curve, is now actually 0. So that means the open circuit voltage on the DC side is then 0, and theoretical calculation is also matching to what we're simulating here. This may not be the case that we always have an open circuit voltage here. We will almost always have a load connected to there, so we need to find a way how we can match the real operating conditions here. The thing is that the continuity of current has to be certified here on the output side, so that we can match our theoretical calculation to the simulation. Let's take an inductor and connect it to the DC side. Let's give this value to the L load, and I'll define the variable here. That's the 1 millihenries. And let's rerun the simulation again to see the effects. So we still have a firing angle of 90 degrees. So there is an error. Let's check where it is. L load is not defined. Oh, okay. Of course, I missed an L here. Rerun. Check. So we see still we do not get the output voltage 0. The reasons we need to have an active source, or if we have a very large inductance like say 1000 millihenries representing 1 henries, and let's rerun it. And now we should be able to see the output voltage to be around 6. So the idea is that you should have an active source on the DC side in order to see the inversion effect. Another way is to add a DC source. Let's do it here. Okay, let's connect it here. DC source, and let's name it to be E. And I include the variable here, E. So 2000 volts. Let's check the values here. So now you see the DC side current, it's charging up the inductor. And important also here is to note that the output voltage is again 0. So the idea is that to add an active components on the DC side. So if this is the scenario, if we want to go to the inversion mode, we need to increase the firing angle beyond 90 degrees. So let's take 135 degrees and rerun. Now the output voltage should be entirely negative as expected here. So you see we have the output voltage to be 1432 and with a negative sign before. And if we want to check it to our theoretical calculation of the output voltage, let's do it here. So we had the variable VDC, it's minus 1431 volts again. Let's go to the extreme value of alpha that would invert the output voltage, which is 180 degrees. Now don't forget that we have a lossless system here. That means we didn't really consider any passive components of the grid and all the transformer and also for the converter. So it's an ideally operating converter system. So we can consider the extreme firing angle of 180 degrees without the necessity to consider extinction angle, which I will discuss later. But let's go with 180 degrees and see the output voltage. Now see, it's only now the DC volt. To see that extreme inversion, let's take the output voltage here, I mean the source voltage to be 0, and check if it is, okay, it is now 0, shouldn't be. So to see the effect of this inversion with lossless converter system with 180 degrees, it should work, and it should give a DC value calculated according to this formula. Let's rerun, should be the correct value. So VDC is minus 2025 volts. So this is actually the correct one. So I apologize for the confusion. We had to add this negative voltage source here in order to see the inversion effect of the converter. Now what it means that when the angle is greater than 90 degrees, then the DC side source is now acting as the generator. Since the current cannot reverse due to the orientation of the thyristors, voltage can, and in that case the power would be reversed. That means the DC side is now feeding power to the AC side. If we try to check another angle like 100 degrees, and let's check the values again. So we have the DC value of minus 351, and the theoretically calculated DC value would be then 351. So there is a good match of the theoretically calculated DC voltage and the simulated DC voltage. So In the next video, let's discuss how to implement the closed loop control for the converter system. Thank you.